You ever wonder how your body, or for that matter, a giant industrial reactor, doesn't just fall apart under stress? Well, it turns out there's a fundamental rule for that, a kind of chemical pushback that keeps everything in balance. So let's get right into it. Okay, so our story today doesn't start in a lab with bubbling beakers. Nope, we're starting on the world's highest mountains with a genuine life or death puzzle. And the only way to solve it is with one single, really powerful principle of chemistry. I want you to picture this. You're a climber, way, way up, thousands of feet. The air is incredibly thin, almost dangerously low on oxygen. But somehow, your body adapts. It feels like magic, but it's not. It's this incredible, high-stakes chemical balancing act happening inside your blood literally every single second. So that brings us to the big question, right? When your environment totally changes and suddenly gives you way less of what you need to survive, like oxygen, how does your body's chemistry actually fight back to keep you alive? Well, to figure that out, we first need to understand what our bodies are trying to protect in the first place. Yeah, so before we can really get how the body fights back, we need to talk about the state it's desperately trying to protect. It's a special kind of dynamic balance called chemical equilibrium. Most of us think chemical reactions just go one way and then stop. But a lot of the time, that's not what happens. You've got a forward reaction where reactants turn into products, and at the same time, you've got a reverse reaction where the products turn right back into reactants. Equilibrium is that perfect sweet spot where both of those reactions are happening at the exact same speed. So from the outside, it looks like nothing's changing, but underneath, oh, it's constant action. This is the perfect way to picture it. Seriously, imagine you've got two water tanks connected by a pipe. Equilibrium isn't when the water stops moving. Not at all. It's when the water is flowing from tank A to tank B at the exact same rate that it's flowing from B back to A. The water levels stay perfectly stable, even though there's all this movement happening. That's the key. It's a dynamic balance, not a static one. Okay, so we've got this perfect dynamic balance. But what happens if you mess with it? What happens if you just dump a bunch more water into one of those tanks? Well, that's where the hero of our story comes in, the principle that explains exactly what happens next. And here he is, French chemist Henri Le Châtelier. And just so we're all on the same page, it's pronounced Le Châtelier. This is the guy who figured out the fundamental rule of this chemical pushback. And this is his core idea, and honestly, it's so beautifully simple. It just says that when you put a stress on a system that's in equilibrium, the system will respond by shifting in a way that relieves that stress. It's like nature's built-in rule for always trying to get back to its happy place, its comfort zone. So what does it actually mean to stress a system? What are we talking about here? Well, in chemistry, it really just boils down to three big changes you can make. Okay, the three big stresses you can put on a system at equilibrium are changes in concentration, changes in temperature, and changes in pressure. Let's break each one of these down. First up, concentration. And this one is probably the most intuitive. Let's say you add a bunch more of a reactant on one side. The system basically goes, whoa, way too much of this stuff, and it speeds up the reaction to use it up and make more products. And of course, the opposite is true. If you dump in more products, the system will shift back the other way to make more of the original reactants. Here's a classic example for you. You've got hydrogen gas and iodine gas in a nice equilibrium with hydrogen iodide. Now, what happens if you suddenly pump a ton more hydrogen gas into that container? Well, the system is stressed. To get rid of that stress, it's got to use up that extra hydrogen. So it grabs some iodine and makes more hydrogen iodide. The whole balance shifts over to the right to find a new equilibrium. All right, next up is temperature. Now, the easiest way to think about this is to literally treat heat as if it's a product or a reactant in the equation. So if a reaction gives off heat, that's what we call exothermic. Then adding more heat is just like adding more product. And what does the system do? It shifts backward toward the reactants. The other direction, the endothermic direction, to basically use up that extra heat and cool things back down. Make sense, right? And finally, for gases, we have pressure. And I love this analogy. Imagine a really crowded room. If the walls suddenly started closing in, shrinking the room and increasing the pressure, what would people do? You'd all squish together into smaller, tighter groups to take up less space, right? Well, a chemical reaction does the exact same thing. You crank up the pressure, and the reaction will shift to the side that has fewer gas molecules. It's trying to relieve that pressure by taking up less room. Okay,
We have all the tools we need now. We get equilibrium, we get the three big stresses. So let's go back to our climber on that mountain and finally solve this mystery of how they survive in thin air. And it all comes down to this one crucial equation. See, in your blood, you have hemoglobin, we'll just call it HB, and it's in a constant state of equilibrium with the oxygen you breathe. Together, they form oxyhemoglobin, and that's the molecule that actually carries the oxygen to all your cells. This right here, this is the delicate balance your body is fighting to maintain.
And here, this is where it all comes together. So you're at high altitude. The oxygen concentration plummets. That's stress number one. The equilibrium shifts to the left, which means less oxygen is binding to your hemoglobin. That's a dangerous condition called hypoxia. But then the body pulls off this absolutely brilliant countermove. It starts producing more hemoglobin. See what it did? It added more of a reactant. That's a new stress, pushing the equilibrium back to the right. And this forces more of that scarce oxygen to actually bind, allowing the climber to get just enough to survive. It is a perfect, real-world example of Le Chatelier's principle in action.
So you see, this principle isn't just for chemists in a lab. It's a fundamental rule for how pretty much any system in balance responds to stress. It explains how giant industrial processes are made super efficient, and it's even why your thermostat keeps your house at the right temperature. Once you start looking for it, you see this push and pull, this constant fight for balance absolutely everywhere. So I'll leave you with this. Think about it. From natural ecosystems to global economies, where else do you see systems fighting to get back to balance?